Hi everyone. In this section we are in 2.11 Power Factor Correction in Three-Phase Circuits. Here you can see a three-phase load which is connected to a three-phase circuit, and you also can see a bank of capacitors which are connected in a star. So the power factor correction in the case of three-phase circuits is quite similar to the one as we have already seen in single-phase circuits. So here, if we consider this diagram here, and we consider a three-phase load which is going to have an inductive power factor, that means that it absorbs reactive power, the capacitor bank will need a tripolar switch here that allows the connection and disconnection of the bank. So, when the capacitors are disconnected, the power factor of the assembly will be the active power of the load divided by square root of the sum of the square of the active power plus the square of the reactive power. When we close the switch, then the capacitors are going to generate a reactive power which verifies the following. The complex power of one capacitor is going to be the phase voltage multiplied by the conjugate of the current that flows here into one of the capacitors. That is the same as applying Ohm's law here. The current in one capacitor could be obtained as the division of the phase voltage divided by the impedance of one particular capacitor and the conjugate of that result. As the capacitor only has reactive power, this is the same as this expression here, because the capacitor only has reactive power and its impedance is only reactance. So if you introduce here the absolute value of the reactance of a capacitor, which is 1 divided by the angular velocity and the capacitance, then you will get to this expression here for the reactive power of one of the capacitors which are here connected in star. So it is minus the angular velocity multiplied by the capacity and the square of the phase voltage. If we want to use the line voltage instead of the phase voltage, you will need to use the expression here which relates both of them. As you have three capacitors, then the total reactive power will be 3 times this reactive power, okay? So this is the total reactive power depending on the line voltage. So if we connect the capacitor bank, then we are going to inject this value of the reactive power in the system. So we are going to decrease the reactive power that the loads are absorbing in this value. So if in this expression you know the final power factor that you want, then you can solve here and obtain the capacitance of the capacitor that we need to change from an initial power factor up to a final power factor. And that will be given by this expression here. If the capacitors are connected in a star, their impedance is going to be 1/3 the impedance in delta. So if you introduce the values here, you can relate the capacitance connected in a star with the needed capacitance when the capacitors are connected in delta. And you are going to get to this result here. The capacitance needed when the capacitors are connected in delta is going to be 1/3 the capacitance needed when the capacitors are connected in star. With this, now you can solve the following examples, which are example 4 and example 5.
Hi everyone. In this example, which is example number 4 of lesson 2, we have a balanced load connected in a star in a three-phase system. So we have here the impedance of the load, which is 10 plus J10 ohms. So they ask two questions. In the first one, they ask about the power factor of the load in the initial situation. That is a very simple question. As we have 10 as the real part of the impedance and 10 as the imaginary part of the impedance, here we have the angle of the impedance, and the power factor would be the cosine of that angle. So that is 10 divided by the square root of 10 to the square plus 10 to the square, which gives a result of 0.707. And they say that this load is inductive. That means that this load absorbs reactive power. Now that we have solved question A, we know that the power factor is this one. We have to solve question B. In question B, they say that we need to calculate what is the capacitance of the capacitor needed to have an ideal power factor equal to 1. If you have a look at the notes in lesson 2, you will find that to compensate the reactive power that a particular load needs, we have to install a capacitor in parallel with that particular load. So here the capacitor will generate the reactive power that the load is going to absorb, and then we are compensating the reactive power in our particular installation, okay? And we can improve our general power factor. So then you can understand that if I want a power factor equal to 1, that means that the power factor of this unit here, which is the load in parallel with one capacitor, this power factor should be 1. And the same should happen with the other loads which are connected in the other phases of the star. So this would be the same representation as represent here a capacitor in parallel, here another one. So, what do we have then? You can understand that if we focused in this particular assembly, one load in parallel with one capacitor, we can get the equivalent impedance of that. As we have two components connected in parallel, the equivalent impedance would be the impedance of the load multiplied by the impedance of the capacitor and divided by the sum of both of them. As you know, the impedance of a capacitor can be expressed in binomial notation as minus j multiplied by 1 divided by the angular velocity and the capacitance. Impedance of load 1 multiplied by impedance of the capacitor and divided by the sum. If you do this calculation, you are going to obtain, here in the real part, you are going to obtain minus 10 j to the square divided by the angular velocity and the capacitance. And in this term, you are going to obtain minus 10 divided by angular velocity and capacity and multiplied by j. Here you will have 10 in the imaginary part, and here 10 minus 1 divided by angular velocity and capacity in the imaginary part. 10 divided by the angular velocity and the capacitance minus 10 divided by angular velocity and capacitance. And that divided by this. So this will be the equivalent impedance of one load connected in parallel with one capacitor. As we want that the power factor of that equivalent impedance is equal to 1, what we want here is, as you can imagine, the result of this expressed in polar notation would be R, the absolute value, and phi, the angle. And as the power factor is 1, that means that phi should be equal to 0 radians. Why is that? because the cosine of phi that gives 1 should be 0. So, if the angle should be 0, what are the implications of that? Well, you understand that here you have a complex number and you can have that expressed in polar notation. There, in the denominator, you could have another value which is also expressed in polar notation. As you know, if we divide these two complex numbers to get to this one, and whose angle is 0, then what we should have is that the angle in the numerator minus the angle in the denominator should be equal to 0. That means that the angle in the numerator and the denominator, they should be the same angle. So, as we want that the angle is the same in the numerator and denominator, we can express the following. The angle in the numerator is going to be arctangent of minus 10 divided by angular velocity and capacitance divided by this. This is the angle in the numerator. The angle in the denominator is going to be this, the imaginary part, divided by the real part. As both angles are the same, let's say that the arguments of these two arctangents are equal. Here in this part, as you can imagine, the result is minus 1. And in this other part, I have this divided by 10. Then if we solve, we can have here minus 10 equal to 10 times angular velocity and capacitance minus 1 divided by angular velocity and capacitance. So then, if I continue solving, I will have minus 10 multiplied by angular velocity and capacitance should be the same as 10 angular velocity and capacitance minus 1. So finally, minus 20 angular velocity and capacitance, and here minus 1, which gives a capacitance equal to 1 divided by 20 times the angular velocity. That is 1 divided by 20 times 2 pi multiplied by the frequency. In Europe, our frequency is 50 Hz. A capacitance equal to 0.0001592 farads, which is approximately the same as 159.2 microfarads. So, each of the capacitors that we need to install here in parallel with this load, the following and the following in each of the phases, each of them must have a capacitance of 159.2 microfarads. In this video, we are going to explain example 5 of lesson 2. So we have an electrical system in which the loads are a motor, a lighting system, and some computers. And the first question asks the total complex power absorbed by this assembly of loads. That would be the sum of the complex power of the motor plus the lighting system plus 3 times the complex power which is absorbed by one computer. So this is what we need to do in question A. Regarding to the motor, we know that its power is 10 kilowatts and its efficiency is 70%. That means that the absorbed power is going to be 10 kilowatts divided by 0.7, which is approximately 40,285.7 watts. We also know that the power factor of this motor is 0.8. So here, if we represent the power triangle, where you have the active power, reactive power, and apparent power, we know this angle here. So as we know this angle here, you know that the tangent of the angle would be the reactive power divided by the active power. So the reactive power is the active power multiplied by the tangent of the angle. So reactive power by tangent of arc cosine of 0.8, which gives in voltamperes reactive. So now we have the value of the complex power of the motor in voltamps. We also need to obtain the complex power of the lighting system. Their power factor is equal to 1, and then their power is 5,000 watts. So the complex power would be 5,000 plus J0 voltamps. Regarding to the computers, we know that they are capacitive loads. Apparent power is 500 voltamps, and whose capacitive power factor is 0.9 capacity. So then we can get the expression of the cosine of the angle would be the active power divided by the apparent power. So the active power is apparent power multiplied by the cosine of the angle. That gives 500 multiplied by 0.9, 450 watts. Now that we have the active power, the reactive power would be square root of apparent power to the square minus active power to the square, which gives 217.9 voltamperes reactive. So that means that the apparent power of the computers, of one computer, will be this one. Remember that their units are voltamps. If we want to obtain the total complex power, we need to assume the complex power of the motor plus the complex power of the lighting system plus 3 times the complex power of one computer. This expressed in binomial notation, which is the same as this expressed in polar notation. So then, if they ask the active power of the assembly, that would be this expressed in watts. They ask the reactive power, it would be this expressed in voltamperes reactive. In question B, they ask the line current in one of the phases that are supplying the system. In order to calculate the line current, you need to use this expression that you have in the notes, which is the total complex power is 3 times the phase voltage multiplied by the conjugate of the line current. So if you solve for the conjugate of the line current, there you will have the complex power divided by 3 times the line voltage. And here, as you know, the phase voltage would be the line voltage in absolute value divided by square root of 3, which gives a value of approximately 230 volts. Okay? The statement gave you that this value was 400 volts, so this is approximately that value. If we consider this phase voltage as reference phasor, there we have 0 here and volts. The conjugate of the line current is this one. So the line current, we need to change the sign of the angle to minus, and we are going to get to this current in the line conductor. In question C, they say that we need to connect a bank of capacitors in delta. and that we want that the final power factor is equal to 1. And we need to know the capacitance of these capacitors, each of these capacitors connected in delta. As the total reactive power was this, as you can imagine, each capacitor must compensate. Each capacitor must compensate 1/3 of this total reactive power, which is this. The impedance of one capacitor was 1 divided by the angular velocity of the capacitance minus 90, which is the same as this. If we apply the Ohm's law, the current in one capacitor is going to be the voltage divided by that impedance. If we consider the system connected in a star, because it is easier, because the voltage would be the phase voltage, we will have 230 volts divided by this impedance here, which gives a current of, if after that you use the expression of the power, then you have that the complex power of one capacitor should be this one, and you have the voltage, considering that we are in star connection, multiplied by the conjugate of this. If then you group the values, you will get this. And if you solve for the capacitance, you will get this. You will get this in farads, which is approximately the same as 201.8 microfarads. So this is the capacitance, but from the beginning we have considered that the system, the capacitor, was connected in a star. And the reality is that the problem asks about the capacitance if the capacitor is connected in delta. So there is a formula which relates the capacitance in star with the capacitance in delta. And it is that the capacitance in star divided by 3 gives the capacitance in delta connection, approximately 67.27 microfarads. So this is the capacitance of each of these capacitors when they are connected in delta.